Multidentate ligands. So what they are, they're ligands that they can form more than one dative bond to the metal ion. Now you might think, oh well, water could be, you know, a bidentate because it's got two lone pairs on the oxygen, but of course the angle involved, it only means that only one of those can ever form a lone pair to a metal ion. So the ones the multidentate ones you really need to know about are diaminoethane. Okay, so we've got the diaminoethane. So you have CH2, and you have at each end an NH2 group. Of course, there's a lone pair on the nitrogen, so it's very like ammonia. We've seen ammonia as a ligand, yep. Well, this is like you've almost got like two ammonias stuck on this ethene bit in the middle, and they can form, each one of those nitrogens can form a dative bond. Okay, so let's have a look at how that would work with copper. Okay, so you can form, well, the formula of it would be Cu H2N CH2 CH2 NH2. Now, how many of them would you need? Well, copper 2+ always forms, well, usually forms 6 covalent bonds. So each one can form 2, so you'd need 3 of those. Yeah. It's important to read, what would the coordination number of the coordination number of the copper ion be? The coordination number would be 6, because that's the number of dative covalent bonds that forms it, not the number of ligands. Right, let's try and draw what that would be. It would be an octahedral shape. So if we draw our there's our flat bit. Here's copper, and so there's going to be 4 bonds like this, 1 down and 1 going up. So I will just draw my diaminoethane like this. I'll just draw N, and then there'll be a CH2, and then the other N there. So you get one ligand like that, and you get another one here with these two, and the third one here. Okay, so I practiced drawing that. They do ask you to draw that sometimes, and there'll be 2+ charge. Well, I put it on the copper, but of course it's shared over the whole thing, really. They do ask you to draw that. Now, interestingly, if you draw a mirror image of that, so you imagine, I'm not going to bother drawing it, but if you did draw a mirror image of that, I might as well draw it, I suppose, then you would see, you might be able to see anyway, without drawing a model, that they are non-superimposable mirror images of each other. So that means they are basically, the complex can show optical isomerism. So a mirror image of that, then, right, I'm going to have one of my ligands here, the other one here. Sorry, not there. I want this one here, and finally that one there. Okay, so those two are optical isomers. They're non-superimposable mirror images, and that's just one little bit. If you look in the specification, it says you do need to know that when you have a bidentate ligand and it's forming a coordination number of 6, you get those two things which are non-superimposable. Right, another bidentate ligand we need to know about, and is the ethane dioate ion. So that is basically the ion from ethane dioic acid. So there is ethane dioic acid, ethane dioic acid, sorry. Right, gives away the protons to form the salt. Right, and that, they can form, they've got lone pairs on the oxygens, they can form dative bonds to the central ion, so that can form complex ions as well. There's one we really need to know about, and it's a hexadentate ligand. That means it forms 6 dative covalent bonds from one molecule, and it is related to the diaminoethane structure. So I'll just put, if you start off with diaminoethane here, that would be diaminoethane. So, sorry, missing off the nitrogen there. That would be diaminoethane, and each of those, the lone pair on each nitrogen can form a dative bond. And what happens in EDTA is you have basically an ethanoic acid. Instead of a hydrogens here, you have sort of an ethanoic acid group. The sodium salt of it, so that's a minus charge there. Now that one, you've got lone pair there, that can form a dative bond as well. And then you have another, you have 4 of these ethanoic acid groups. There's another one. And then you've got 2 on this side as well, so we'll get rid of them. And 1 on this up here. Okay, so you've got lone pairs on those. There. Right. Sorry. There. Now, you don't have to remember how to draw that, but they do quite often ask, they'll do it, and they'll say circle the where the dative bonds are formed from. So it's not that difficult to remember. Everything is diaminoethane with 4 ethanoic acid groups stuck on it. Its name is EDTA, and no one, I had to actually look it up to remember what EDTA stands for, so don't worry about it. It stands for ethane diamine tetra acetic acid, and acetic acid is the old-fashioned name for ethanoic acid, but don't worry about that. Okay, and very often EDTA is written down like this with a 4 minus, okay, because you've got 4 negative charges on it, as shown there. But it can form 6 bonds. Now that's quite important. So that means you only need 1 EDTA molecule for each. You know, you've got most metal ions have a coordination number of 6. You only need 1 ligand to do all that covalent bonding. So let's think with copper again. We're always using copper, but it could be iron or could be anything. If you have copper, hexaqua, so 6 waters there. You're only going to need 1 EDTA to react with it. And it's going to form this complex, Cu EDTA. And the charge on that is now going to be 2 minus overall, but 2 plus on the copper, 4 minus on the EDTA. But importantly, you're going to get 6 H2Os. All right, when you do that, you do get a subtle change in color. So this stuff is copper, of course, is kind of a pale blue color. And when you do that, it goes a little bit darker. Okay, it's not a really dramatic change, but you do notice it goes a little bit of a darker blue color. And when you change the ligand, you need to always change the color. Now, this reaction is irreversible. All the other ligand exchange reactions we've looked at so far, they're reversible. So, for example, if you've got our copper hexaqua and we add conc hydrochloric acid to that, you go to you will form that CO4, and that's 2 minus, and you get 6 H2Os coming off there. Right, this was, you remember, this is blue, and this is a nice green color. So if you, to make it go forwards, you add HCl, And Le Chatelier's principle, if we want to make it go backwards, well, we're just going to add lots of water. If you add water, it will try and use up the water, and of course it'll go back to being blue. Okay, and that's reversible. But this EDTA reaction here is irreversible, and we're going to see why now. And it's all to do with entropy. So if you haven't done entropy yet, don't worry about it too much now, but you might want to come back to it when you have done the thermodynamics topic. Right, let's have a look at this, the entropy disorder. Okay, so on this side of the equation, we have got two aqueous species. Yeah. On this side of the equation, we have got 6 waters and 1 iron, so we've got 7 species there. So what has happened is delta S, the entropy has increased. So delta S for that is positive. Right, now if you go to our delta G equation, oh, by the way, delta H for this experiment, for this reaction, is approximately 0. There's not much in it at all, and that's because you break 6 covalent bonds and you make 6 bonds which are about of the same strength. So it's, there's not much of an enthalpy change at all. Let's think of our delta G expression. What's delta G? So delta G is equal to delta H minus T delta S. Now for this reaction, we've seen that this is approximately 0. Delta S is positive. So that means this whole thing here is negative. So that means delta G for this reaction is negative. And of course, if it's negative in the forward direction, delta G will be positive in the backward direction. So that means it can't happen. Reactions where delta G is positive are not thermodynamically, they're impossible. So that means that reaction will not go backwards. So once you have formed the copper EDTA complex there, that's it. It stays in that. And this is this is called the Chelate effect. Okay, so we'd say that copper EDTA, or that complex, is called a chelate. That means you've got 1 molecule of EDTA. I think chelate means crab, and it's like a like a crab's claw closing around the copper. That is called a chelate, and we could say that the Cu has been chelated. That means it's basically taken out of circulation, and it can't do anything else. So EDTA is used for quite a lot of things. It's used for in a lot of cleaning solutions because it will remove metal ions. It's also used to stop blood clotting, because EDTA will also react with calcium ions in blood, and calcium ions are required for the clotting cascade. So if you take blood in a hospital, you stop before it can be processed in the lab, you have to put something in it to stop it clotting, otherwise it just turns into a big solid clot, and EDTA is sometimes used for that. If you look in shampoo bottles and things like that, quite often you'll find there's EDTA in them, so it's kind of everywhere. The important thing is when it forms this complex with an ion, it's irreversible. Right, that's about all we need to know about polydentate ligands. So we'll leave it there.